Greetings A-level chemists, welcome to today's video where we're going to be looking at the reduction of carbonyls, so in particular butanone. So butanone is a ketone and we're reacting it with acidified KCN, so this is going to be a nucleophilic addition reaction, and we've got to highlight this mechanism and draw it out. Okay, so first we'll start with the mechanism and then we'll show why the product doesn't show optical activity. Okay, so this is what butanone looks like. First thing to do is add your partial charges, okay? So this group is polar, so the carbon is delta plus and the oxygen is delta minus. So this means it can be attacked by nucleophiles. So nucleophiles have a lone pair of electrons and they are going to be attracted to positive charge. We've got a positive charge on that carbon center. So the nucleophile in this case is my nitrile ion, and remember it's the carbon that has the negative charge and the lone pair of electrons, okay? So as the CC bond forms, this CO double bond has to break, okay? So that opens up, forming this intermediate. So now I'm going to draw it with the CN attached, and that bond is broken. So we've got some H plus kicking around because it said it's acidified potassium cyanide, and then what happens is we form a bond with that O and that H, forming my hydroxynitrile. And there you go. So this is a nucleophilic addition reaction. And there is the mechanism. So we need to know this for for AQA and Edexcel. Now, great follow-up question is to justify why the product formed above doesn't exhibit optical activity, and we need to give a detailed explanation. So, just redrawing butanone, this is what butanone looks like. What I'm going to do when I draw it out below is I'm just going to condense this group to C2H5, so it's an ethyl group. Okay, so when I draw it, you've got to remember that the carbonyl group is planar because that carbon is sp2 hybridized, and if it's trigonal planar, the CH3 is going to be like that, and here is my C2H5. Okay, so what happens is when the cyanide ion attacks, and I'll try and do it in two different colors, and if that's a plane, it can attack from either side, from above and below the plane, and that attack is equally likely. Okay, so my cyanide ion can attack from this side, you can say that's below, and then it can also attack from above. Now, the likelihood of that is 50-50, so we got 50% chance of the nucleophile attacking from one side and 50% chance of the nucleophile attacking from the other side. And what does that mean? This means that if it attacks from above, I'm trying to think, let's see if I can show this in a slightly better way. Okay, so I've just drawn it a different way and hopefully this makes a little bit more sense. So as the cyanide ion attacks from above, this is what we'd get. And I'll draw the product of this reaction. So we get that carbon there, and at the top we're going to get the cyanide ion, okay? So it's got a 50% chance of attacking above the plane. And then this oxygen there, whoop. Give me 1 second. This oxygen there is going to be in the plane of the board. Okay, so that's in the plane of the board. Now, I'm just going to put that as OH because we did the reaction mechanism on the previous question, okay? So this C2H5, or this ethyl group, is going to be coming out of the page. So there's my ethyl group. And then this CH3 is going away from me, so that's as a wedge. Sorry, a dash. Okay, so that's option A. If we have a look at option B, where the nucleophile attacks from below the plane, well, let's draw this out. So we've got an equal chance of the nucleophile attacking from below the plane and attacking that partially positive carbon center. And if that happens, we will get this. This could work out really nicely if get it to work. So then, there is my central carbon. Here is my cyanide coming from below the plane. And then this oxygen is in the plane. I'm just going to put it as OH. And then this ethyl group is coming out towards us. And that CH3 is going away from us. Okay, at the moment you might be thinking, what on earth is going on? But let's see if I can convince you. So what we're going to do is we're going to take option B. And then we're going to place it next to option A, and then we're going to rotate the molecule. So if I rotate the molecule, have a look at what happens. These guys are actually mirror images. These guys are actually mirror images. Okay? Because I've got a nitrile group here and I've got a nitrile group here. This OH is reflected. This ethyl group is also reflected over here, and I'm going to write it so it's not upside down. So that's coming out towards us. Coming out towards us, coming out towards us. And that CH3, which is going away from us on the left-hand side, is also going away from us on the right-hand side. So they're mirror images of each other that are non-superimposable. So if you want, I'm going to draw this methyl group in the same way. So, first of all, let's think, do we have a chiral carbon center? Yes, we do. We have a chiral carbon center. Why do we have a chiral carbon center? Because I have 4 different groups attached to it. Same on the other side, that's a chiral carbon center. I know my C is opposite, but there you go. So I've got 4 different groups attached to it, so I have a chiral carbon center. Okay, and then I've generated mirror images in the reaction because this molecule, the carbonyl group, is trigonal planar. So that means the nucleophile can attack from above the plane and below the plane. Both of those are equally likely. And that means the product is a 50-50 mixture of enantiomers, which we call a racemic mixture. So I get a 50%, I don't know whether it's the R or the S, I'm just going to say R, and I also get 50% of S. So the net effect is you get no net rotation of plane polarized light, so it doesn't show optical activity because they cancel each other out. So that's the theory. Let's show this in practice. The CO group is planar. So there's equal chance that the carbonyl group is attacked from above and below the plane, resulting in or producing a racemic mixture of both enantiomers, the left-hand version and the right-handed versions. So they're not going to show any optical activity because they're going to cancel the rotations out. Okay, really nice question. Thanks for watching. Ta-ta.